Okay, welcome all of you. So we have been discussing about NOE concepts since last 2 or 3 classes. It is a vast subject and we had to discuss extensively. Varieties of things we discussed about NOE, and then in the last class we discussed about types of NOE experiments, starting with steady state NOE, HOESY, HOSY, ROESY, varieties of things we said. And then NOE experiment also has some complications. We saw that what happens in the case of when you do the 1D NOE, steady state NOE, I wanted to show how we can do it. You selectively saturate a spin and then collect the signal. Go very much off resonance, identical RF power you apply, take it as a reference spectrum, take the difference, you see the signal. And then there will be some complications, you have to be extremely careful. So the selectivity of the saturation is very important. If you don't selectively saturate a signal, if you perturb the neighboring signal, there is a leakage of RF, then you will get wrong results. Sometimes it could be confusing. Also, if you have a multiplicity pattern, you have to uniformly perturb them. Otherwise, what will happen? You will create an antiphase character, and that when you take the area may get nullified finally. You may not be seeing the NOE, although it is there. That's also I saw that, I told you. And I told you about the 3-spin effect. If you have 3-spin ABSC, if it is linear or angular, you are irradiating A and see this effect on B, and B will be leaking to C, and then because of that leakage, there may not be a correct NOE for that. If it is the angular thing A to AC, if you want to see NOE, it may be leaking through B also. That's also possible. It may so happen, instead of getting positive NOE, it may be leaking to B and may get nullified also. So varieties of things we discussed. In the HOSY, I took the example of some HOSY of fluorine and proton and lithium and proton, etc. It could be area of the heteronuclear other dilute spin, doesn't matter. So when the HOSY was seen, I showed you that there is a cross peak which is very easy to interpret. In the HOSY case, there is it not symmetric, spectrum is not symmetric. Whereas in the case of the NOESY, it will be always symmetric. I will not discuss about the 2D NOESY, I will discuss in the next class or in this class itself. Then I took the example of ROESY. Why the ROESY comes? Because omega tau C1 is approximately equal to 1 for certain molecules. Then there is a condition situation at which NOE goes to 0. When NOE goes to 0, then what do you do? So we can alter the condition, physical conditions, either go to higher magnetic field, or change the temperature, change the solvent, etc. Change the tau C or change the omega. That is in your hands. Alternately, an experiment has been designed where NOE can be done in the rotating frame. That's what I said. Rotating frame NOE is always positive, never goes to 0. We discuss varieties of advantages of ROE, how it happens. The source spin irradiated and the other spin where which the magnetization transfer takes place are both along z axis plus and minus z in NOE. But in the case of ROE, you do it in the transverse plane. It is plus x and plus y and minus y, plus x or minus x. They are opposite to each other like antiphase. And then magnetization transfer takes place. And important thing I told you, in the NOE case, gamma B0 if you consider, B0 is the static field. In the ROE case, B1 is the RF field, which is much smaller compared to B0. As a consequence, it is like you can treat like always extremely narrowing conditions. So these are the things which I observed in the case of ROE also. And I showed you there is a 2D ROE pulse sequence. I may not be able to show the 2D because the time is getting short, too many things to talk. But I showed you 2D ROESY sequence. We will continue with it today. This is a 2D ROESY sequence here. And of course, there is a T1 period followed by spin lock. In the spin lock, what happens? I told you already. Chemicals should get completely refocused and mixing takes place between the spins, and then you collect the signal. This is a simple example of a 2D spectrum of a molecule like this, 2D ROESY spectrum. This is called ROESY. What is transferred there? Don't worry, I didn't discuss too much about those things. Why I am showing this is, when you do ROESY, what is the pulse sequence you use for TOCSY? Identical. To ROESY sequence and TOCSY sequence are almost identical. We saw that. The apply TOCSY experiment when we did 1D TOCSY or 2D TOCSY, I showed you there is RF pulse, mixing pulse, and then we vary the T1 and the mixing pulse and collect the signal. We saw that. There is no difference between the TOCSY sequence and ROSY sequence. Both have spin lock. But then as a consequence what happens? There are examples where in the ROSY you get TOCSY peaks. This is a simple classic example to show the molecule, where you can see this is an experiment where ROSY is done in a different way, which I tell you what it is slowly. Then you will see lots of peaks here which are present, which are missing here, here. These are all called TOCSY peaks. If you do a conventional experiment of a 2D, you are going to get a ROSY spectrum along with TOCSY peaks which are dominant. In this case, TOCSY peaks are removed. How we can remove that? I will tell you now. These complications come in the ROSY. TOCSY transfer takes place, that occurs during spin lock. COSY peaks also can arise from J coupling. There is signal attenuation from off resonance effects. There is a multi-step transfer involving both TOCSY and ROE stages that can give us to false ROEs. All these complications can come. Okay, so somehow, especially TOCSY peaks, everything that can give rise to complications. We need to somehow overcome that. How do you overcome that? These are the problems you come across. These really. For example, I have a hypothetical molecule like this. B to C, there is close in space. I want to see, I am expecting ROE here. You may get it. That is a genuine ROE between B and C. But it can so happen there can be a TOCSY correlation between TOCSY transfer of magnetization from A to B and then B to C. This is a false AC ROE you may get. It may not exist, but you may see ROE. Also it can so happen there is a transfer of magnetization from C to B and B to A, there is a TOCSY transfer, and then you will see as though C to A ROE is there. Here it will see A to C ROE because of transfer of magnetization this way, but it can go other way, then you will see there is a ROE as if between C and A. These are all complications in ROSY. Okay. And then another few important things you should know is signs of the cross peaks in ROSY. Because ROSY, and I will tell you later, exchange spectroscopy, XE, and then TOCSY, all these peaks will come into the picture here. See, this is the signs of cross peaks in ROSY experiment relative to diagonal peak if you consider. Conventional diagonal peak is always phase positive. Consider ROSY. This is a ROSY cross peak. And I will say direct ROE if it is there, cross peak is negative. With respect to diagonal, I am talking. Diagonal is positive. And then indirect ROE, 3 spin effect is there. We saw that A to B, B to C, or C to B, B to A, in which case it appears positive. There can be a toxic correlated peaks, in which case if diagonal is positive, cross peak is also positive. Through the TOCSY there can be an ROE, in which case diagonal peak is negative. This is a false ROE. There can be ROE and TOCSY. We saw that in the previous example, A to B, B to C, or C to B, B to A. Both cases are discussed here. In both the cases, NOE is negative. I mean, the sign of the cross peak is negative. So as a consequence, there we have a false ROE. There can also be chemical exchange, and the sign of the cross peak is positive. There can be COSY type peaks. We have mixed phase, antiphase, and in phase. All these things can happen, and then to overcome that, there are certain methods. Firstly, you can apply a very low power RF for spin locking, very low power, comparable to maximum resonance frequency offset. That we don't need to use the higher one. That's one way. Alternately, you can use pulse spin lock. It's a continuous RF CW. You can apply pulse with a delay like this, repeat n times, and this pulse, this can be angle less than 90 degree. N number of times you apply for the same time period, mixing time period. You apply n number of such series of pulses, that is a spin lock you are doing in a pulsed manner, not a CW manner. That can also help. Alternately, you can apply what is called alternating phase spin lock like this 180, now you are now 180 plus x, 180 minus x, like that. You repeat it n times like here. Then what will happen? This is called a transverse ROE. What will happen once the magnetization is here? Goes here. And see, this will come here, this will come here. This magnetization which are opposite to each other, one is the source spin is here and the other spin is here. They are all opposite to each other in plus y and minus y axis. They keep changing their positions. Once this comes here, this goes here. Every time when you apply 180 plus pulse and 180 minus x pulse, this trajectory keeps changing. This is called tick-track trajectory. You can do tick-track trajectory, make the spins to follow. Then you are going to get what is called, this is called a transverse NOE. This is another easy way to overcome some of these problems. Because where toxic peaks coming and everything can be overcome. Many of these problems can be overcome by modifying this thing. Okay, this is with this I will be almost completing the concepts of NOE, but I will show you here the peak spectrum which I wanted to show here earlier. This was, I told you, with the toxic dominated ROE, toxic peaks are dominated. This is what is transverse ROE. Transverse ROE. What is transverse ROE? Where the spin lock pulse is 180 plus x and 180 minus x, continuously n number of times you apply, tic-tac trajectory follow. Then these toxic peaks are largely suppressed. This is a transverse ROE. So these are all some of the tricks which you have to follow. So basically I have given you a lot of concepts about NOE, OESY, ROESY, steady state NOE, everything. A lot of things we discussed. Hopefully you have got a point about what we have to do, which type of experiment you have to do, how do you overcome some of these complications, etc. And with this we will really jump into some few experiments. So far I was telling you, of course, only this example of 2D ROESY and OESY I showed. Homonuclear 2D NOESY I have not shown at all. You will really see the 2D experiment. That is called transient NOE. I discussed steady state NOE, ROESY, OESY, but transient NOE I did not discuss. Transient NOE can also be done in the 1D way by using gradients. I am not worried about that, I am not discussing that, but I will discuss 2D NOE, that is called NOESY. That is another important thing. So with this we will go to a different topic now altogether, okay, and we will see what is NOESY and everything. Okay, we will go into the NOESY experiment. Where is it? Okay. So we will start now discussing about what is called two-dimensional NOESY, which is also called transient NOE, TRNOE. Okay. We already discussed steady state, we discussed OESY, we discussed ROESY. Now we will discuss NOESY. It is a two-dimensional experiment, not one-dimensional experiment, that is steady state NOE. Now what is the difference here? In the case of NOESY, NOESY is a non-selective experiment in nature. In the case of steady state NOE, you remember I told you selectively you have to saturate one of the spins and see the effect, magnetization transfer to the neighboring spin. Selective, you have to do one by one. This is non-selective in nature. All NOEs to all the protons can be mapped in a single experiment. That is an advantage. So it is a non-selective experiment. Here NOE is built up during a short mixing time with the spins relaxing along z axis, and the spins will be relaxing going back along z axis because it is a ZZ magnetization transfer. I told you if this magnetization transfer takes place for NOESY along z axis. This provides accurate distance information if you use build up curve for the measurement. If you can do several NOEs with a different T1, how it builds with the mixing time. If you monitor that, you can get a very accurate distance information by using this type of experiment. And most effective at determining rough estimate of relative proximity of protons. up to 5 to 6 angstrom, you can almost get a rough estimate of the distance. That is very effectively you can do that. Okay. Of course, if you want to do precisely, you have to do the build up curve, take the build up curve. Here the recycle delay between the scans can be very short, unlike in the steady state where we have to give a long, 3 times, at least 3 times T1 of the spins, which is taking long time to relax. And the artifacts are much smaller here than in steady state NOE. That is the advantage. Not many artifacts will be there. In the steady state I showed you, depending upon selectivity of excitation and all those things, we got lot of problems there. All those things can be overcome. There are still be there, but very minimum here. Artifacts are minimum here. What is a 2-dimensional experiment? NOESY. It consists of a 3-pulse sequence like this. Very simple. What it does? You apply 90-degree pulse and then bring the magnetization to x axis or y axis, apply another 90-degree pulse and then allow the spins to mix here with the mixing time. Then I apply a pulse, detection pulse, and start collecting the signal. This is what happens. During the T1 period, the transverse magnetization, let us say I am doing proton and OE, transverse magnetization of protons, the protons evolves in the transverse plane in the T1 period. The magnetization of protons after applying 90-degree pulse are brought here, they start evolving in the xy plane. Okay. Apply 90-degree pulse, it creates longitudinal magnetization, because the magnetization what was there in the x axis or y axis, they will be taken back to z axis, because there is a 180 pulse, 90 plus 90 it will be with a delay of course. As a consequence, spin vectors would have moved by some distance in T1. And then magnetization transfer allow them to mix up in a mixing period. There is a magnetization transfer by a cross relaxation, chemical exchange, whatever it is, that can take place. And apply a last pulse which creates transverse magnetization and FID is detected. This is a simple way. And the magnetization transfer for 2 spins A and X that are close in space. How it happens? Like this. Bring the magnetization from Z axis to Y axis. Allow for the time T1 to spins to start moving. They start processing, and they move by certain degrees based on the T1, how much you wait. Now the both, let us say spin A and X, X and Y component of the spin A is there. Vectors have started moving with T1 like this. Apply another 90-degree pulse. Then this component will come to this, move like this, and I am considering only the component along Z axis. So other spin, let us say I am not considering, only one of them I am considering. A, I am not worried about. X spin, let us say green remains same, just for the sake of understanding. And this component of the magnetization, only I am considering one which comes here. This one would have moved other far away. I am not worried about that. Only one of the component is taken, and give some time for mixing for a few seconds. Few milliseconds, don't give seconds. What happens during the mixing time? The spins with their macroscopic magnetization along minus Z axis here, minus Z axis will, what do you mean by that? Minus Z axis means they are in the excited states. From alpha to beta state it has gone. That means they have higher energy. They have to go back to a ground state or go to the equilibrium state by giving excess magnetization to somebody. They have to get rid of excess magnetization. The spins which are along minus Z axis in the excited state will come back to plus Z axis by giving magnetization, getting rid of the excess magnetization. Where does it give? It will give to the neighboring spins. That is what happens. The magnetization is transferred to neighboring spins that are close in space. How it can happen? Because of dipolar relaxation. 2 spins close in space experience dipolar relaxation. That is why, remember I discussed about dipolar relaxation, how this one of the spin keeps moving with all across, keeping their orientation same. It creates a local dipolar field at the site of the other nucleus, which is responsible for relaxation, that fluctuating dipolar field I discussed that. So now because of that, what will happen through the dipolar relaxation, the magnetization is transferred from one spin to other. This is what happened during the mixing time. During the mixing time, magnetization is a minus z, come back to z axis, and it gives magnetization to spins which are already along z axis through dipolar relaxation. And give some time, NOE will start building up slowly like this. Slowly Z magnetization build up and give magnetization to X, and now apply 90 pulse. X magnetization which along Z come to transverse plane and start doing the Fourier transformation. You will get that signal. This is what happens. You understand the concept? Bring the minus magnetization to minus Z axis by applying 90 pulse T1, another 90 pulse. Take worry about the component of the magnetization along minus Z axis. It is an excited state. It has to give its energy, lose its energy, get rid of its excess magnetization by giving it some other spin which is along Z axis, which are closed in space through dipolar relaxation. That spin is also along Z axis, and then slowly there is a build up of magnetization of the other spin. If you do the apply third 90 pulse and do the Fourier transformation, you get a signal for that other spin. I inverted A, but I got magnetization along signal for X. This is what happened during mixing time. There is a transfer of magnetization from proton A to proton X. And pictorially, how the enhancement comes, a crude diagram I am giving you as a function of increasing T1. Let us say you have inverted the magnetization Z. I have written X spin is here, it has some magnetization. Then you start giving this comes down, gives magnetization. Then there is some dipolar relaxation also going on. It will take magnetization, it comes down. Then this goes up, this goes up, this. Finally, see, completely minus Z, it goes to Z axis, and this give all its magnetization to X. See, A spin, red spin will give to blue spin. It follows a trajectory, oscillates. The X spin enhancement oscillate at the spin of A, frequency of A. A spin magnetization comes down, goes up, comes down, goes up like this. And then this magnetization energy keeps coming down, it does not go to negative, it oscillates. This oscillates at the frequency of A spin. Now NOESY cross peaks. Where do you get the NOESY cross peaks in 2D? NOESY cross peaks are generally between two chemical ships, between two nuclei that are close in space. As I told you, there is no need of a J coupling between them. Only close spatial proximity is very important. NOESY peaks appear as artifacts in 2D NOESY spectra. Artifacts are removed by phase cycling of the first two pulses. There are NOESY artifacts appear in the NOESY spectra, but you can remove that by doing phase cycling. There are several ways of removing this thing. Okay, there are a lot of improvements are there in the pulse sequence. So NOESY cross peaks are symmetric with respect to diagonal, similar to your COSY, TOCSY. NOESY is also symmetric with respect to diagonal. And intensity of the cross peaks qualitatively give you information about the spatial proximity. Higher the intensity, they are very close in space. The spins are far away separated in space, the intensity comes down drastically. And if they are very far away, there may not be any intensity at all, there may not be any NOE at all. So qualitatively, you can say, looking at the intensity of the cross peak, you can find out about this close spatial, find out about the spatial proximity, whether they are close or not. Approximately, you can get qualitatively. Of course, how do you get quantitatively? That is a different thing. You should know that. If you want to get it, you have to monitor the built up curve, everything. That is what I told you while discussing the concepts. Assuming that you know how to do NOE, you understood NOE, 2D NOE, the transient NOE, everything. How do you use it? Okay, this much concept is understood. You are doing transient NOE. All peaks you can get in the NOE at a time. It is not a selective thing. It is at a time non-selective. All the NOEs wherever whichever there in the molecule can be simultaneously obtained. We are using a 3-pulse sequence. I am not discussing much about more gradient varieties of modifications are there. I am not discussing that. Only NOESY spectrum, how do you interpret the NOESY spectrum? Simple NOESY spectrum. We will take couple of examples. I am taking NOESY spectrum of a simple molecule, cis-pentene. How do you interpret that molecule? How do you interpret the NOESY spectrum? Of course, NOESY we are using it to get the conformation information. We will see that. This is a NOESY spectrum of cis to pentene. This is structure of the molecule. All the protons have been numbered. Where you can interpret the spectrum without any difficulty, because we know that this is proton 5 and the high field region. It is a triplet because of CH2. This CH2 is a quartet because of this, and each lane of the quartet is coupled because of this geminal coupling. It can also have a trans coupling. I do not know whether it has a cis coupling, they are far away, 1, 2, 3, 4 months, 5 months away. I do not know whether it is there, but anyway complications are there. What I am trying to say is interpretation is not that difficult, not that easy. Although molecule is simple, of course qualitatively by using some idea we can say which peak is which, but multiplicity pattern everything we can understand differently. First of all, what is important is identifying, making assignment of the different protons here. Let us start assigning the peaks here. First of all, there are 5 protons. You see there are 5 protons here. 2 are overlapped. 5 groups of protons are there. COSY we have discussed and we know how to make the assignment. Start with this one of the peaks on the diagonal, come vertically down, go horizontally, go vertically, completed the square. I know this proton and this proton are coupled. This is proton 5, this is proton 4. In the previous example, this is proton 4 and the next one is the third one. This is proton 4 is here. That is why I said it is so complex. It has coupling with various things. Okay, that is also done. Proton is coupled to, we have understood 5 and 4 assignment we have made. What next? If you carefully see, this 4 has a cross peak here, go across, complete the square. Then that has to be 3. But you can see that 2 and 3, there are 2 peaks which are overlapped, not resolved. There is not enough of resolution for us to say, but they are there. But then that one of the peak gives a correlation to other one and complete that square. I would say this is proton 1. So if I go systematically, I know 3 to 2, this 5 to 4, then we understood 4, 3, 2 and 1. COSY spectrum we already analyzed n number of spectra in the class in this course earlier. So we have understood how to interpret this. That is fine. What next? We will take the NOESY spectrum of the same molecule. It is very interesting. If I take the NOESY spectrum of the molecule, this is cis-pentene. We have to see what are the cross peaks we are seeing here. There is one cross peak here. Remember, this was not seen in the COSY. There was one cross peak here between 1 and 4. This cross peak. See here 1 and 4, there was no cross peak. So as a consequence, this is a NOESY peak. There is a cross peak between 1 and 4. H4 and H1 correlation is seen in the NOESY spectrum. What does it tell me? These two are close in space proximity. That is why it is giving cross peak. There is a cross peak between 1 and 4 because they are on the same side of the double bond. If this CH2 were to be here and this proton were to be here, of course multiplicity pattern here would have been different. That is a different question. CH3 would have been doublet instead of a triplet. But nevertheless, we do not know whether this one is on this side or the other side. We do not know whether cis or trans. But when these two are close to each other, there is a spatial proximity is so close, there is a correlation between these two. So CH3 and CH2 is going to give cross peak here. That confirms for me it is a cis geometry, because these two are on the same side of the double bond, then these two protons should be on the other side of the double bond. They are on the same side. This establishes cis geometry for the molecule. So, you now understood how we can use the NOESY spectrum to get the conformation structure of the molecule. Now I can confidently say, looking at the NOESY peak, these two protons are on one side of the double bond and these two groups, and these two protons are on one side of the double bond, establishes cis geometry for the molecule. And also you can see H2 and H3 correlation. That is another confirmation. Look at this here. H2 and H3 correlation is there in the NOESY. But unfortunately, they are not resolved because the chemical shifts are so overlapped. If there is a cross peak between these two, you can see 2 and 3 are also correlated through space. There is a confirmation that 2 and 3 are also on the same side of the double bond. These two together establishes cis geometry for this molecule. Okay. Okay, I will take one simple example before we complete. The time is getting over. I will take this last example to see. Maybe I think since time is up, I will take this example in the next class tomorrow or so. So I am going to stop here. But today, what we did, we started with the complications we get in the ROESY cross peaks, and varieties of problems we can think of. It comes because of the TOCSY peaks could be there, everything. How do you overcome that? We saw that if there are TOCSY peaks, we can use, instead of CW, we can have a pulse mixing time or tick-tock sequence, 180 plus x, 180 minus x for the mixing, entire mixing period, repeat it n times for the duration of the mixing. Then TOCSY peaks are removed. Partially you will eliminate them. And we saw very clean spectrum for the ROESY where TOCSY peaks were removed in one of the examples we saw. Then subsequently, we thought after that we should go into real application, real 2D NMR, NOESY. There are varieties of NOE experiment I told you, steady state NOE, HOSY, ROESY, which we discussed. And in this class we started discussing NOESY. I told you NOESY is the 3 pulse sequence, 90 T1 90, mixing time 90, start collecting the signal. And we saw in the the T1 period when you bring the magnetization start evolving in the T1. Then again after a 90-degree pulse, it will as a part of the magnetization, one of the component of the magnetization vector goes to minus z axis. We look at the component of it, and then because it is in the excited state at minus z axis, it wants to get rid of its magnetization by giving it to other spin, which is closed in space. That's we saw pictorially how it happens. It gives magnetization to the neighboring spin only through dipolar interaction there. Dipolar relaxation is there. It relaxes by giving its magnetization to spin which is closed in space. We saw that one. That's how it works actually. So then finally, if you do the experiment, 2-dimensional Fourier transformation, you are going to get a NOESY spectrum which is symmetric with respect to diagonal, like our COSY and TOCSY sequences. That's what we saw that. And of course, we want interpretation of that is very, very easy. I showed you. TOCSY peaks can also have, I told you, several complications. It can give us to COSY peaks, many things will be there. But then we have to use a judicious ties to discuss and then identify the cross peaks. I didn't go into more details of that, how to do and everything. But remember, there will be complications, but those can be minimized by some methods. And you are going to get, we will look at only the cross peaks. We took the example of Cis-pentene and we saw cross peak between two CH groups which established that they are closed in space because they were giving NOE cross peak. The same molecule, other two protons on other side, they were unresolved and they also give rise to cross peak. This establishes the spatial proximity of these three groups and establishes cis geometry for the molecule. That's what we understood. So you can utilize the NOESY in getting the information about the geometry of the molecule, conformation of the molecule. So that's what we can use a NOESY for. I will give you few more examples and specific examples in the next class. So I am going to stop here. Thank you very much.